You clicked on this video to understand quantum physics, and you're in the right place. We're breaking it down into simple terms, so by the end you'll have a solid grasp of the fundamentals. Imagine a world where the familiar laws of physics dissolve, and a reality far stranger than fiction takes hold. A world where particles can be in two places at once, where reality is a matter of probability, not certainty. This is the captivating realm of quantum physics, a field of science that delves into the very heart of matter and energy, exploring the fundamental building blocks of the universe. Quantum physics isn't just a theoretical pursuit confined to laboratories and textbooks, it's the foundation upon which our modern world is built. From the smartphones we use to the lasers in our CD players, quantum physics is the invisible force driving countless technologies we rely on daily. Yet despite its profound impact on our lives, quantum physics remains shrouded in mystery for many, often perceived as an intimidating and inaccessible subject. In this exploration of the quantum world, we embark on a journey to demystify its complexities, peeling back the layers of enigma to reveal the elegance and wonder that lie beneath. We'll navigate through the fundamental principles that govern this strange realm, using vivid analogies and captivating visuals to make these abstract concepts accessible to all. Join us as we unravel the secrets of the quantum realm, venturing into a world where the impossible becomes possible, and our understanding of reality is forever transformed. To truly appreciate the revolutionary nature of quantum physics, we must first understand what it seeks to explain. In essence, quantum physics is the study of the universe at its most fundamental level, exploring the behavior of matter and energy at the atomic and subatomic scales. It's a realm where the classical laws of physics, those that govern the macroscopic world we experience daily, break down and a new set of rules takes over. These rules, often counterintuitive and mind-boggling, have challenged our understanding of reality since the early 20th century, leading to a paradigm shift in scientific thought. One of the key distinctions between classical and quantum physics lies in their approach to understanding reality. Classical physics, rooted in determinism, posits that the behavior of objects can be predicted with absolute certainty if we know their initial conditions and the forces acting upon them. Quantum physics, on the other hand, introduces the concept of probability and uncertainty. It tells us that at the quantum level, we can only predict the likelihood of an event occurring, not the event itself. This inherent randomness, far from being a limitation, is what makes the quantum world so fascinating and unpredictable. This shift from a deterministic to a probabilistic view of reality is just one of the many conceptual leaps required to grasp the essence of quantum physics. Another key concept is wave-particle duality, a mind-bending principle that suggests particles, like electrons and photons, can exhibit both wave-like and particle-like behavior. This duality, experimentally verified through numerous experiments, challenges our classical intuition, which neatly categorizes entities as either waves or particles. Imagine a beam of light, which we typically perceive as a wave. Quantum physics tells us that this beam of light can also behave as a stream of particles called photons. Conversely, electrons, which we traditionally think of as particles, can also exhibit wave-like properties, such as diffraction and interference. This inherent duality is a fundamental aspect of the quantum world, blurring the lines between our classical categories and forcing us to embrace a more nuanced understanding of reality. Another pillar of quantum physics is the Heisenberg uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a particle with absolute precision. This principle, far from being a mere limitation of our measurement abilities, is an intrinsic property of quantum systems, highlighting the fuzziness and uncertainty that permeate the quantum realm. These are just a few glimpses into the strange and wonderful world of quantum physics, a world that challenges our classical intuitions and invites us to rethink our understanding of reality. We'll delve deeper into these concepts, exploring groundbreaking experiments like the double-slit experiment, which vividly demonstrate the baffling nature of quantum behavior. We'll also uncover the mysteries of quantum entanglement, a phenomenon that connects particles in a way that transcends distance, allowing them to share a fate even when separated by vast stretches of space. Our journey into the quantum realm is just beginning, and as we venture further, we'll encounter even more mind-boggling concepts and awe-inspiring discoveries. So fasten your seatbelts and prepare to embark on an unforgettable adventure into the heart of reality, where the familiar dissolves and the impossible becomes possible. Quantum physics, a profound departure from classical physics, ventures into the realm of the extremely small. Energy, momentum, and other quantities are restricted to discrete values. Imagine energy as tiny indivisible packets like grains of sand. This concept, introduced by Max Planck, forms the bedrock of quantum physics. Quantum mechanics describes and predicts the behavior of matter and energy at the subatomic level. It's like a rule book governing fundamental particles. Quantum mechanics provides the mathematical tools to understand these phenomena. Quantum physics doesn't render classical physics obsolete. Classical physics still holds true for the macroscopic world. It governs the motion of planets, projectiles, and fluid flow. Classical physics is like a city map, providing a broad overview. Quantum physics is like a detailed street map, zooming into intricate details. Both are essential for a complete understanding, each providing a different level of detail. The development of quantum physics wasn't a singular event but rather a gradual evolution of ideas, fueled by a series of groundbreaking experiments and theoretical breakthroughs that challenged the very foundations of classical physics. The journey began in the late 19th century with the discovery of phenomena like blackbody radiation and the photoelectric effect, which classical physics failed to explain. These anomalies hinted at a deeper, more fundamental theory governing the behavior of matter and energy at the atomic level. In 1900, Max Planck, in an attempt to explain blackbody radiation, proposed that energy was not continuous but rather quantized, existing in discrete packets he called quanta. This revolutionary idea, initially met with skepticism, marked the birth of quantum physics. 5 years later, Albert Einstein, building on Planck's work, explained the photoelectric effect by proposing that light, too, was quantized, consisting of discrete packets of energy called photons. This duality of light, exhibiting both wave-like and particle-like behavior, shattered the classical view of light as solely a wave phenomenon and laid the groundwork for wave-particle duality, a cornerstone of quantum physics. The following decades witnessed a flurry of discoveries and theoretical developments that further solidified the foundations of quantum mechanics. Niels Bohr, with his model of the atom, introduced the concept of quantized energy levels for electrons, explaining the stability of atoms and the discrete nature of atomic spectra. Werner Heisenberg's uncertainty principle highlighted the inherent fuzziness of the quantum world. It showed the impossibility of knowing both position and momentum precisely. Erwin Schrödinger's wave equation described quantum systems, cementing wave-particle duality. These pioneers revealed a universe governed by probability and uncertainty, where observation influences outcomes. Their work revolutionized our understanding of the universe, paving the way for lasers, transistors, and medical imaging. This phenomenon, known as the double-slit experiment, vividly demonstrates the wave-particle duality of matter, a cornerstone of quantum physics. It suggests that particles like electrons do not follow well-defined paths like tiny marbles, but rather exhibit wave-like properties, spreading out like ripples on a pond. Another key concept bridging the gap between classical and quantum physics is the correspondence principle, proposed by Niels Bohr. This principle states that the predictions of quantum mechanics must converge with those of classical physics in the limit of large systems or high energies. In essence, the bizarre quantum effects become less pronounced at larger scales, and the familiar laws of classical physics emerge as a limiting case of quantum mechanics. Think of it this way. A single wave in the ocean may seem chaotic and unpredictable, but a large collection of waves, viewed from a distance, exhibits a more predictable pattern, like the ebb and flow of tides. Similarly, the probabilistic nature of individual quantum events averages out at larger scales, giving rise to the deterministic behavior we observe in the macroscopic world. The correspondence principle provides a reassuring link between the familiar world we experience and the strange realm of quantum phenomena, demonstrating that quantum mechanics does not invalidate classical physics, but rather encompasses and extends it. The journey into the quantum realm is an ongoing adventure, with new discoveries and technological advancements constantly pushing the boundaries of our understanding. From quantum computers promising to revolutionize fields like medicine and material science to quantum cryptography offering unprecedented levels of security, the implications of quantum physics are far-reaching and transformative. Embracing the quantum revolution requires a willingness to challenge our preconceived notions about reality, to step outside the comfort zone of our classical intuitions, and embrace a world where the impossible becomes possible. It's a world where particles can exist in multiple states simultaneously, where information can be teleported instantaneously, and where the very act of observation can influence the outcome of an experiment. As we delve deeper into the quantum realm, we uncover a universe more bizarre, more wondrous, and more full of potential than we could have ever imagined. It's a universe that challenges our understanding of reality, but also offers unparalleled opportunities for exploration, discovery, and technological advancement. The quantum revolution is here, and it invites us to embark on a journey that promises to transform our world in ways we are only beginning to comprehend. Imagine a world where the very nature of reality is blurred, where the familiar distinction between waves and particles dissolves into a perplexing duality. This is the essence of wave-particle duality, a cornerstone of quantum physics that challenges our classical intuitions and forces us to rethink the fundamental building blocks of the universe. In the macroscopic world we experience, waves and particles are distinct entities. Waves, like ripples on a pond, spread out over space and time, carrying energy and momentum without transporting matter. Particles, on the other hand, are localized entities like tiny marbles, possessing a definite position and momentum at any given time. Quantum physics throws this neat categorization out the window, revealing that particles, like electrons and photons, can exhibit both wave-like and particle-like behavior, depending on how they are observed. This duality, experimentally verified through numerous experiments, suggests that the very act of observation can influence the nature of reality at the quantum level. Think of it this way. Imagine a beam of light passing through two narrow slits. If light were purely a wave, we would expect to see an interference pattern on a screen behind the slits, with alternating bright and dark bands representing regions of constructive and destructive interference. This is indeed what happens. Imagine firing individual electrons one by one at two slits. Classical physics predicts two distinct bands on the screen. Astonishingly, we observe an interference pattern. Each electron seems to interfere with itself. This highlights the wave-particle duality of matter. Electrons exhibit wave-like properties, spreading out like ripples. Their waves interfere, creating the observed pattern. The double-slit experiment establishes wave-particle duality. Particles can exist in a superposition of states. The Heisenberg uncertainty principle challenges our notion of certainty. Formulated by Werner Heisenberg in 1927, it limits the precision of certain pairs of properties. Imagine pinpointing the location and speed of an electron. Classical physics suggests we could predict its trajectory. The uncertainty principle disrupts this view. The more precisely we measure position, the less precisely we know momentum. This is an intrinsic property of quantum systems. Imagine trying to illuminate a tiny, fast-moving particle with a powerful flashlight. The brighter the light, the more precisely we can pinpoint its location. However, the light itself, composed of photons, carries momentum. When these photons collide with the particle, they alter its momentum unpredictably. So, the more precisely we try to determine the particle's position, the more we disturb its momentum. This trade-off between position and momentum uncertainty is a fundamental consequence of the wave-like nature of quantum particles. The uncertainty principle has profound implications for our understanding of the quantum world. It tells us that at the subatomic level, we cannot predict the future with absolute certainty. Instead, we can only calculate probabilities for different outcomes. This inherent randomness isn't a flaw in our theories, it's a fundamental aspect of nature. Prepare to have your mind bent by one of the most bizarre and intriguing phenomena in quantum physics: entanglement. If you flip these entangled coins and one lands heads up, you instantly know the other must be tails up, even if they're miles apart. This correlation isn't due to some mysterious force acting between the coins. It's a consequence of their shared initial state. Similarly, entangled particles share a single, unified quantum state. When we measure the state of one particle, we're essentially collapsing this shared state, forcing both particles into definite but correlated states. This correlation persists, even if the particles are light years apart, seemingly violating the principle of locality. Entanglement suggests that the universe is far more interconnected than we previously thought. This interconnectedness has fueled research into quantum teleportation and quantum cryptography. In the quantum realm, the impossible becomes possible, and one of the most striking examples of this is quantum tunneling. The probability of tunneling decreases exponentially with the thickness and height of the barrier, but it's never zero. This means that even for seemingly insurmountable barriers, there's always a chance, however small, that a quantum particle can tunnel through. Quantum tunneling plays a crucial role in numerous physical phenomena, from nuclear fusion in stars to the operation of transistors in our electronic devices. It's also the basis for scanning tunneling microscopes, which allow us to image surfaces at the atomic level. Quantum tunneling is a testament to the weird and wonderful nature of the quantum world. Prepare to enter a world where particles can exist in multiple states simultaneously, defying our classical intuition about the nature of reality. This is the realm of quantum superposition, a mind-boggling concept that lies at the heart of quantum mechanics. Imagine a coin standing on its edge, spinning rapidly. It's neither heads nor tails, but rather in a superposition of both states simultaneously. This is analogous to a quantum particle in superposition, existing in a combination of multiple states at once. In the quantum world, particles don't have definite properties until they are measured. Before measurement, they exist in a blurry, probabilistic state, encompassing a range of possibilities. At the heart of quantum physics lies a seminal experiment that has captivated and baffled physicists for over a century, the double-slit experiment. This seemingly simple experiment provides a profound glimpse into the bizarre and counterintuitive nature of the quantum realm. Imagine a setup where a beam of light is shown upon a barrier with two narrow slits cut into it. Behind the barrier, a screen captures the light that passes through the slits. If light were simply a wave, we would expect to see an interference pattern on the screen with alternating bright and dark bands, and indeed, this is what we observe when the experiment is performed with light. As the electrons are fired one by one, a remarkable pattern slowly begins to emerge on the screen, an interference pattern, the hallmark of wave-like behavior. The double-slit experiment forces us to confront a profound mystery. How can particles, seemingly solid and localized entities, exhibit wave-like properties? The answer lies in the concept of wave-particle duality. Particles like electrons do not follow well-defined trajectories. Instead, they exist in a superposition of states. When an electron is fired towards the two slits, its wave function passes through both slits simultaneously, creating an interference pattern on the screen. The act of measurement collapses this wave function, forcing the electron into a definite state. The double-slit experiment highlights a crucial aspect of quantum mechanics. The observer and the observed are inextricably linked. The double-slit experiment, with its profound implications for our understanding of reality, has sparked countless debates and philosophical inquiries. It challenges our classical intuitions, forcing us to question the very nature of particles, waves, and the act of observation itself. Despite the profound mysteries surrounding quantum mechanics, the theory has been incredibly successful in predicting and explaining a wide range of phenomena. Its technological applications are ubiquitous, from lasers and transistors to medical imaging and nuclear energy. Some physicists embrace the strangeness of the quantum world, accepting that the universe operates under rules that defy our classical intuitions. Others seek a more intuitive, deterministic understanding of quantum phenomena. Regardless of the interpretation one subscribes to, the double-slit experiment stands as a testament to the power of human curiosity and the relentless pursuit of knowledge. The strangeness of the quantum world has profound implications for our understanding of the universe and our place within it. Quantum computers, for example, leverage the principles of superposition and entanglement to perform calculations that are impossible for classical computers. Quantum cryptography exploits the principles of quantum mechanics to create unbreakable encryption keys, ensuring secure communication. By encoding information in the quantum states of photons, quantum cryptography guarantees that any attempt to intercept or eavesdrop on the communication will alter the quantum state. Quantum sensors offer unprecedented sensitivity and precision in measuring various physical quantities. These sensors have the potential to revolutionize fields like navigation, medical imaging, and environmental monitoring. The concepts of superposition and entanglement challenge our very understanding of reality. The philosophical implications of quantum mechanics are equally profound, raising questions about the nature of reality and the role of the observer. These questions, once confined to the realm of philosophy, are now being tackled by physicists and philosophers alike. The answers, if they are ever found, promise to revolutionize our understanding of the universe and our place within it. The journey into the quantum realm is an ongoing adventure, with new discoveries and technological advancements constantly pushing the boundaries of our understanding. The quantum revolution invites us to embrace the unknown, to challenge our preconceived notions about reality, and to explore the universe with a sense of wonder and awe. The mysteries of the quantum realm represent an unparalleled opportunity for discovery, exploration, and the expansion of human knowledge. The journey ahead promises to be challenging, exciting, and ultimately transformative. As we conclude our journey into the heart of quantum physics, we find ourselves standing at the precipice of a new scientific era. The strange and counterintuitive world of quantum mechanics has now taken center stage, driving technological advancements and reshaping our understanding of the universe. We've delved into the depths of wave-particle duality, where particles dance between existence as waves and particles. We've marveled at the implications of the uncertainty principle, which reminds us that the universe possesses an inherent fuzziness. The interconnectedness revealed by quantum entanglement has left us pondering the true extent of the universe's interconnectedness. And the concept of superposition has challenged our very notion of reality, suggesting that the universe is a vast tapestry of possibilities constantly unfolding before us. Quantum physics is more than mind-boggling concepts. It's a rapidly evolving field with the potential to revolutionize our lives. The quantum revolution is driven by advancements in quantum computing, cryptography, and sensing. Quantum computers promise to solve humanity's most pressing challenges. Imagine personalized medicine with new drugs tailored to individual genetics. Envision materials engineered at the atomic level, revolutionizing energy and manufacturing. Quantum cryptography offers unbreakable encryption, crucial in an era of cyber threats. Secure communication channels are paramount as we rely more on digital data. Quantum cryptography ensures privacy and security of our digital lives. Quantum sensors can revolutionize medicine, navigation, and environmental monitoring. Imagine medical imaging detecting diseases at their earliest stages. Envision GPS systems guiding autonomous vehicles with pinpoint precision. The quantum future is bright, filled with possibilities that were once relegated to the realm of science fiction. As we continue to delve deeper into the quantum realm, we can expect even more astonishing discoveries and technological breakthroughs, forever altering our understanding of the universe and our place within it. However, the quantum revolution also presents us with profound ethical and philosophical questions that we must grapple with. As we gain the ability to manipulate the very fabric of reality at the atomic level, we must proceed with caution and foresight, ensuring that these powerful technologies are used responsibly and ethically. The journey into the quantum realm is not merely a scientific endeavor, it's a journey of self-discovery, a quest to unravel the mysteries of the universe, and to understand our place within this grand cosmic tapestry. It's a journey that requires us to embrace the unknown, to challenge our preconceived notions about reality, and to approach the universe with a sense of wonder and awe. So, let us continue to explore, to question, and to marvel at the wonders of the quantum world. Let us embrace the challenges and the opportunities that this new era of scientific discovery presents, remembering that the journey itself is just as important as the destination. The quantum future awaits, and it's up to us to shape it wisely, responsibly, and with a deep appreciation for the profound mysteries that the universe continues to reveal. If any part of this video sparks your curiosity, drop your questions in the comments. We'd love to discuss them. Thank you for joining us on this journey on basics of quantum mechanics. Please like and share the video, and please do not forget to subscribe for more videos.